Welcome to a curious puzzle on an infinite grid. We start with 6 red prison cells, but only one of them contains a character called A. Your goal is to free all the A's using an operation called Q. Here's how it works. You remove one A from a cell and create 2 new A's, one directly above and one directly to the right, but only if both of those target cells are empty. The big question is it possible to free all A's from the red prison cells? Try it yourself at the link in the description. Let's try it. How can math help us understand whether this puzzle is solvable? Let's see what happens when we apply operation Q. Each time we apply it, one A disappears and 2 new A's are created, one above and one to the right. To track this process, we'll assign values to each cell on the grid. Assign values to each cell as follows. Start with 1 at the bottom left cell. As you move right, divide the value by 2. As you move up, also divide the value by 2. So the values go 1, 1/2, 1/4, 1/8, and so on, both across rows and up columns. Here's the key idea. No matter how many times operation Q is applied, the total value of all A's in the grid stays constant. Let's calculate the total possible value across the entire grid. We do this by summing column by column. The first column has values 1, 1/2, 1/4, 1/8. That's a geometric series that adds up to 2. The second column starts from 1/2, then 1/4, and so on, summing to 1. The third column sums to 1/2, then 1/4, and so on. So the total grid value is 2 plus 1 plus 1/2 plus 1/4 plus 1/8. This geometric series adds up to 4. That means no matter how many A's we generate, the sum of their values can never exceed 4. Now back to the puzzle. Let's take a closer look at the value distribution on the grid. The 6 red prison cells together occupy positions with values 1, 1/2, 1/4, 1/2, 1/4, 1/4. That adds up to 2 3/4. But here's the key point. At the very start, there is only one A, placed at the bottom left corner, which has a value of exactly 1. So even though the prison area has a combined value of 2.75, only 1 unit of value is actually in use, and that value must remain constant throughout the process. That means the remaining cells, everything outside the prison, can collectively hold at most 1.25 units of value, since 4 minus 2.75 equals 1.25. This is a strict limit on where the new A's can go. At the start, there is only one A, and it sits at the origin, the bottom left red cell, which has value 1. So the total value of all A's at the beginning is just 1. And since value is conserved under operation Q, this total must remain exactly 1 forever. That means all A's generated through this process must have total value at most 1. Let's examine what happens if we try to place an A in the first column, say at the cell with value 1/8. To create that A, there must have been another A below it, because operation Q only produces A's upward and rightward. But if there's no A below it, then no more A's can exist above it. That means all the other cells above it must remain empty, and their values, which add up to 1/8, are now unusable. The same argument applies to the bottom row. If we place an A at a cell with value 1/8, and there's no A to its left, then every cell to the right must stay empty. So again, we lose at least another 1/8. Together, this means we lose at least 1/8 plus 1/8, which is 1/4 of value just from trying to reach the edge cells. Now let's tie everything together. Suppose just 1A could be freed from the red prison. To make that happen, a whole chain of supporting A's would need to be generated, spreading upward and to the right, across infinitely many cells. But as we've seen, the total value available is strictly limited, and there's simply not enough value to occupy all the cells required to support that one escape. So if freeing even a single A demands an infinite number of occupied cells, that's not possible under the rules. Hence, it is not possible to free all A's from the prison cells. Thanks for watching. If you enjoyed this mathematical puzzle, don't forget to like, comment, and subscribe. We'll see you in the next one.